So this week I want to start talking about the physical analysis. So in our previous two Legion sessions, we've talked about the logical analysis, right, which effectively tries to find, dependencies between operations to figure out which operations can go through the mapping stage in parallel and which operations have to be mapped in order based on, potential data dependencies that they might have and so forth. And the physical analysis is where we actually do run the mapping stage of the pipeline and try to actually map operations onto the actual physical hardware and issue copies and record dependencies and eventually build the realm event graph. So today I want to start that process and start looking at how that works. We're not going to get through it all today, but we can at least begin the process of trying to understand how the physical analysis works. So refreshing everyone's memory, in the previous sets of lectures we talked about logical analysis, and that records dependencies, right, and between the operations. And when those logical dependencies, the mapping dependencies, are satisfied, right, an operation will get this trigger ready call, right, effectively saying that all of your mapping dependencies have been satisfied, so it's now safe for you to begin the mapping process, right? And effectively, most operations will do something like what we're going to look at this map up because it's very simple. It has a single region requirement, and it will make looking at some things a little simpler today. We'll look at tasks in a future lecture, but effectively you get this callback, right? And then usually what you do is you add yourself to the list of ready operations that are ready to map, and you can ask your mapper to go through and map them and so forth. But there's actually something that happens before you enqueue yourself in the list of ready operations to actually go and do the mapping, right? Pretty much all operations will call this perform versioning analysis API call on the region tree first, and it does it passing in its region requirement, and it passes in this version info object, which is effectively getting which is going to store the list of what we're going to call equivalent sets that are going to be used for this physical analysis. We're going to talk about what equivalent sets are today. But effectively, this is like getting some preconditions, for actually doing our physical analysis. It's actually going to go and find all of the equivalent sets. Now, so what are the equivalent sets? Let's take a little digression over here. This is PowerPoint slide over here. We'll actually look at this one first. Right, so Legion allows multiple regions to be overlapping with each other, potentially like regions that are in the same region tree, right? Like I might have this region R1 that's partitioned into two subregions, R2 and R3, and I might have another partition of R1 into two other subregions, R4 and R5, right? Well, Legion has to have some way of knowing what are the most recent physical instances that have valid data for each of those logical regions and stuff like that. And the way that we do that is by having, a group of what we call equivalent sets, which store the metadata for, what are the most recent valid instances, that have valid data based on the other operations that have run for different, points in all of these regions, right? And, so for example, I might have taken this top level region R1 and I broke it into a set of equivalent sets, corresponding to the points 0 to 3, an equivalent set that represents the points 4 to 5 and 8 to 9, equivalent set for 6 to 7, equivalent set for 10 to 14, and equivalent set for point 15, right? And each of these equivalent sets will be a data structure that stores, the most recent valid instances for these sets of points, right? And so if I want to to map a region, for one of my operations, what I do is I find all of the equivalent sets that, are either totally overlapping or at least have some of the points for my logical region. Like if I'm mapping R4, right, I'll need to talk to this equivalent set and this equivalent set and this equivalent set because it has, at least half of the points in this equivalent set as well, right? And I'll sort of interrogate them and figure out, is my instance that I'm trying to map valid for those points? If not, let me make sure I issue an update copy to make sure to bring it up to date from some prior valid instance and issue any prior reductions and things like that. Right, and so mapping a region, say like a region requirement in our let's say we're mapping our inline mapping operation here. It's got a single region requirement, it has some region there. What we need to do is we need to go find the names of these equivalent sets that we're going to need to talk to. And I'm not going to actually show you how this API call works today, because this is actually the thing that I'm currently refactoring, and I want to show you the new version when it's ready. But the important thing to take away is that this is going to go get our set of equivalent sets and store them in this version info data structure. Let me actually show you what that version info data structure actually looks like. First, I'll show it to you on the operations. You can see the type. So like if we look at the mapOp class, there's a version info struct right here. So you can see it has this class version info, and you can actually find this in Legion analysis .h. So if we go look at the version info class, it's actually only got a single thing inside of it. It's actually just a wrapper. It's kind of like a nice wrapper for you just around this one thing. And what you see is that this is a field mask set of equivalent sets, right? Pointers to equivalent sets, right? So, we get a set of equivalent sets or pointers to them, and then associated with each of them, we have a field mask saying which fields those equivalent sets are valid for, right? And in this picture back here, right, you might have one set of equivalent sets for region R1 for one field, and then you might have a different set for another field. And in some cases, fields can share equivalent sets, but that's just a detail. If you want to, you can think of it as like, every field has its own set of equivalent sets, and you need that set and stuff, and we're only combining across fields that share the same equivalent sets, right? So really, this version info struct is just, it's actually a pretty simple wrapper. You can see most of the methods in here are inlines, just for getting references to things like that, and a little support for packing and unpacking these version infos for when you need to move them to other nodes and stuff like that. But effectively, what this call is doing over here in this mapping operation here, right, is just populating this version info with our set of equivalent sets. And you get back a list of these preconditions, which effectively says when this version info has been populated. So this call is actually asynchronous, right? Because it might take us a little bit of time to go off and do the work to actually find those equivalent sets. And in a future lecture we'll see why that's the case. But you get back this preconditions that say when this version info has been populated with all of your equivalent sets, and then use these preconditions to say when you're ready to actually map this this operation, right? And so eventually all these preconditions will have triggered, right? And then that's when we get this call back to trigger mapping saying, effectively, all you're ready to actually do the mapping process for this operation. Now there's a bunch of stuff in here that is specific to inline mappings, but the real important API call here actually happens down here with this this physical perform updates and registration call. And so what this is going to do is this is actually going to go off and actually do the physical analysis to bring this inline mapping up to date, right? And you can see when the return for this call is actually an application event saying, when the instances in the set of things we're trying to map, these mapped instances here, right? These are the instances that your mapper picked. In fact, maybe I shouldn't have skipped over so much of this. I think the actual important thing here is like, maybe one thing I should say here is like, one of the most common cases for this mapOp is you ask the mapper which physical instances it wants to map. It populates this, this set of instances saying, these are the instances that we want to actually bring up to date. And so, we've talked about the mapper in the past. You can go look at this invoke mapper call. It calls out to the mapper manager, which calls the actual, application mapper, which gets us back our instances and converts them back and so forth. And maybe we'll look at some of that in a little more detail later. But effectively, this is the set of instances that we're trying to bring up to date for our particular inline mapping here. And so you see it's calling this physical perform updates and registration call. And one of the things it's passing in is this set of mapped instances that it's going to bring up to date. And then when we get back at the end here is the application event saying, this is when all of your instances are up to date, right? And you can use that to then say that your inline mapping is done, or if you were launching a task, that would be your sort of your precondition to running the task, because that's when your instances are actually valid and ready to be used and stuff like that. And so what we're going to do is we're actually going to unpack this physical perform updates and registration call, at least the first half of it today. One important thing I will show you before we dive into that is this map applied conditions. So similar to how we passed in this set of preconditions up here, This is also an asynchronous call, and so you pass in this set of map applied conditions here, which is a set of we can actually find it here, is a set of runtime events, effectively saying like if you have any asynchronous effects that have to occur as part of this perform updates and registration call, right? Then you can put your your events in the set, and those eventually get fed into if I scroll down here a little bit. There's this mapping applied stuff here, but you can see this mapping applied is just a merge of these map applied conditions, right? Saying, this is the event saying when all of the effects, for our mapping are done, and then that gets passed into this complete mapping. This finalized complete mapping here is just for control application. In the case of a non-control application, it'll just pass through this mapping event case. And that says that we're done with the mapping stage of the pipeline when this map applied condition event has triggered. So, effectively forwarding through all of our asynchronous effects and stuff like that. Okay, so let's actually go take a look at this physical perform updates and registration call, because it's actually quite important. Okay, so physical updates and registration is done on the region tree, so we can actually find it. Physical perform updates or if I can spell correctly. There it is, updates and registration. So you can find that in regiontree.h. If you come over to regiontree.cc, you'll find it right here. And so what you see is this is actually a small helper method. It's actually calling two sub-methods here in the region tree. So the first one is obviously physical perform updates and then physical perform registration. You can see I prefaced everything with physical, so you can keep in mind that you're in the physical stage of the pipeline here doing the physical analysis. And we're going to focus on this perform updates part here today, and we'll probably need to look at perform registration in a future date. But this is just a helper method. Effectively, it calls this first one. This will give you back an RT event saying when all of your updates have been issued. And when I say updates, the thing to keep in your head when it says updates, you should be thinking like realm copies and fills and stuff to actual physical instances to actually update the instances themselves. And so that's actually like updating all of the instances. And then this registration is when we're going to record whatever our operation is here as a user on those instances, right? So like this first part will issue any fills or copies or reduction copies and so forth to bring our instances up to date. And the second thing is going to record ourselves as a user once we've done all those or issued all those copies to Realm, right? And recorded those as users on those instances as well. Then we'll record ourselves as a user on the instances that we're trying to actually map. So that's what these two different things are doing. And we're going to focus mostly on this first part up here, this physical perform updates API call. And you can actually find that one right up here. Okay, here's physical perform updates. You can see it's taking a bunch of arguments. There's the region requirement argument. Here's our version info, right? Storing all of the names of the equivalent sets that we're going to need to talk to as part of our analysis, right? You got an operation, you've got your region requirement index, you've got any precondition events that you might have, like say if you had some external preconditions for running this operation, you might say there was an execution fence that occurred before this operation, you might have a precondition event and so forth. This is the event for the completion of our operation that we're running, saying when we're going to be done running. Here's the set of instances that we're trying to bring up to date. You can think of this as just a list of instances and a field mask for each one of them to say these are the sets of instances that we care about. Let's see. I'm going to ignore the sources stuff. That's effectively a way for your mapper to say, if there are prior valid instances that you want to copy from, you can pre-tell us that as part of your mapper API call, but that's a performance optimization. And what we're going to do is we're actually going to do this analysis. And you can see that we're going to make an analysis object, and we're actually going to return it here. So this is a pointer reference, right? So we're going to create a new analysis object, and this is actually going to be like an output parameter of this method in addition to this RT event, passing that back out to the enclosing context, right? And if I actually show you out here in this physical perform updates and registration, you can see there's a new update analysis here, and it comes out of physical perform updates because it's not actually done here, and then it goes into this physical perform registration. Actually, does this one escape? I don't think that it does. Let's see. Right. It doesn't actually escape. It'll actually end up being deleted as part of it won't actually be needed in this particular case. There's another case where it is needed, so we can actually ignore that here. But anyway, it is an output parameter of this physical perform updates call, this update analysis here. Okay. There is a bunch of debugging code here for checking various different things that we can actually mostly skip over. These are a bunch of invariants that we like to check to make sure that we're not in here if we shouldn't be, like, we're not doing any virtual mappings, and that we're projecting the right kind of region requirement and those kinds of things. You can see we get our region node for the region that we're trying to map here, right? This is our region from our region requirement. We're getting the field mask from our region requirement fields that we actually care about. And the next thing that we're going to do is we're actually going to make this update analysis class. So before, let me take a step back and explain what this update analysis class is actually going to be an instance of. So if we jump over to legionanalysis.h, we can find this update analysis class. And you'll see that this actually inherits from this base collective copy fill class, which inherits from something else. Let's go to the bottom of this type hierarchy here. So you can see collective copy fill analysis inherits from registration analysis. Right, and registration analysis inherits from this physical analysis class, right? And so what you're going to see is this physical analysis class is actually the base class that we actually, for all kinds of analyses that have to be done on these equivalent sets. So these equivalent sets, they effectively provide all the metadata for all these regions. And all the physical analyses that we do, regardless of what kind of operation we're going to do, are going to need to be an instance of this physical analysis class. And this physical analysis class, there's a bunch of stuff here at the top, but really the main thing to look at are these methods down here. It has a bunch of methods to help with actually performing many of the various different operations that you want to perform on these equivalent sets, right? And so, like, one thing that you might want to do is, traverse over a set of equivalent sets and perform the analysis on each one of them, right? So you have this perform traversal method here, which, effectively takes in a version info containing a set of equivalent sets and their mask that you want to walk over, right? It's going to go through and traverse over all of those and then call this perform analysis method, right? And effectively, this is what will actually dispatch to performing the actual analysis on the equivalent sets for whatever kind of analysis we're performing. And I'll just show you briefly in a minute, all the different kinds of analyses that we have for analyzing equivalent sets, or for doing analysis on equivalent sets, right? In some cases, which I will explain also in just a moment, your analyses might actually need to go to a remote node. And we'll talk about why that is in just a minute here as well. And then, this perform updates is when you're actually, once you've finished your traversal, with all of the different equivalent sets, you might need to do something like issue all of your copies that you've decided that you need to do, having traversed all of your different equivalent sets, right? And then, there are other stages for this physical registration or this physical analysis for performing the registration and then performing output in the case of, like, restricted coherence and stuff like that. But that's special cases, and we're going to talk about perform registration in a future discussion. So we'll get into that a little bit later. But you can see these are all virtual methods, and they get overloaded by the various different subclasses that actually perform different things. So there's a couple of different, like, top-level physical analyses that you should at least be aware of, and I'm just going to highlight them very briefly now, and then you can look at a lot of these offline. The main one is perform this update analysis, right? This is the one that actually gets used by most operations to issue copies and fills, to bring the instances that are trying to be mapped up to date. But you can actually find some other ones up here. So for example, here is this valid instance analysis, right? And you can see this actually inherits directly from this physical analysis. And what does this one do? Well, it finds the sets of valid instances and equivalent sets, right? And when do you want to do that? Well, if your mapper asked for the names of the valid instances in the current logical regions, right, as sort of a precondition for doing, like, its mapper call, right? Well, then this is the valid instance analysis that actually gets used for actually performing that. And in particular, like, just to show you a little example of that, Let's see if we can do this on the fly here. Right, so if we look at this invoke mapper call on this map op, right, if the mapper requested these valid instances, right, you can see we have this call physical premap region on the region tree to actually populate the set of valid instances here that the mapper wants to know about for the region requirement. So if you go into region tree.h, let's see, and we search for physical premap region, you can see that one of the very first things that it does is it makes one of these valid instance analysis, right? And then it says, okay, I've got my analysis. I'm going to perform my traversal over all of the equivalent sets, right, for that are stored in this version info, right, and wait for that to be done. And when that's done, then I can report my instances that come back from that analysis, right, and store them, and then the mapper will have access to those names of those valid instances, right. Well, actually, and I should say I actually skipped a stage of the pipeline here, right? If any of the analyses were remote, you might actually send some of those analyses remote, but then you eventually wait for that result, right? And then you can return that back to your mapper and say, hey, here are all your valid instances that you asked for as part of before you do your mapper calls, you can tell the mapper, these are the sets of valid instances, right? Okay, so that's a little digression there. If we pop the stack back, let's see, legion analysis.h. So there's the valid instance analysis. Invalid and anti-valid instance analyses are both here for tracing. They find the set of checking whether instances are invalid or not, or anti-valid, or for like making sure your reductions are not being used and stuff like that. We talked about the update analysis. There are analyses for doing acquires and releases. For doing copy across, for when you have a region-to-region copy with a virtual mapping. You've got override analysis in the cases of things like fills, and you've got filter analyses in the case of doing attaches and detaches and stuff like that. I guess override also gets used for attaches, right? So effectively all these different analyses are the various things that are going to walk over those equivalent sets and update them, right? Effectively do some sort of modifications to the state, of those equivalent sets in order to manifest the physical analysis, right? And so we probably won't go. We're not going to have time to go into all of these today. We'll probably encounter some of these in future lectures. Today we're going to focus on this update analysis because it's by far the most common physical analysis that gets used because pretty much most operations that need to map region requirements, end up using it to issue update copies and things like that. So if we actually go back to region tree.h, let's actually look at, once we make this update analysis, let's look at, some of the stages of these pipelines or of this analysis being performed, and let's talk a little bit about how that works. So let's see, where was my region tree.cc? Here we go. Okay, so we were in physical perform updates, right? So we make this new update analysis, and this is going to be the thing that's going to walk over all of our equivalent sets, right? We actually, so all these analysis are instances of sort of the collectible class, not the distributed collectible, but just the local collectible class, meaning you could effectively reference count them locally inside the node, right? So you add a little reference here to keep it valid until it's done running, right? And the first thing you do is, I'm going to skip this convert view stuff. That's for collective instances and stuff. But you perform this traversal, right? So once you made your analysis, you're going to walk over all of the equivalent sets in this version info, right? And you'll get back an event for when that's actually done. Now, let's see. Let's actually see if we can take a quick look at that. Let's actually search for perform analysis over here perform traversal. Yep. Okay. So, if you got a precondition event, leading into this perform traversal, you can defer it until later and get back a new RT event for when that's ready. But common case, at least in this case, there won't be any preconditions. So you can skip this part. Right. So the first thing you do is you grab your set of equivalent sets out of your version info thing, right? And then what we're going to do is we're going to walk over each of the equivalent sets, in this set. And we're going to call this analyze method, right? And we're passing in, the name of the equivalent set, the fields we want to traverse over, and then this deferral events, saying when the thing will actually be ready right? And then if there's any deferral events, we return those as the result, saying, you know, we deferred this analysis or this analyze call until a later time. So if we go look at analyze, let's see. I might need to search for physical analysis analyze. There we go. Okay, so here's the analyze method on the physical analysis. So we're in the base class here, right? We've got our equivalent set, you know, that we're trying to analyze. We've got the set of fields. We've got some events and preconditions, right? If we've got preconditions, or if we don't have a precondition, we actually go do this now. Otherwise, we can, you know, launch a new continuation meta task to go off and do things. You'll see that pattern a lot here for continuations for doing different things. But you know, the first thing we're going to do is we're actually going to like look at our analysis. Every analysis has a set of points that we're trying to analyze, right? Like in the case of, you know, let's say we're mapping R4 here, right? There's a set of points in an index-based expression that stores the names of all the points for this region R4 that we're going to analyze, right? And, you know, the first thing that we do is we need to find the name of points that we're going to actually analyze this on this particular set, right? And so, you know, if they're the same, right, well, the same expression, well, then we can just use them, right? This is really easy, right? Otherwise, you know, assuming the set is not empty, we'll ignore the empty set case. That's a weird one. But assuming it's not empty, what we do is we intersect, you know, the expression of the points that the set stores with the set of points that, you know, our analysis is being done for, right? And that's necessary to handle stuff like this case right here, where like R4 partially overlaps with the equivalent set storing points 6 and 7, right? Like when we do our analysis over this equivalent set here, we don't want to do the analysis for both points 6 and 7 because, you know, only point 6 is contained in R4, right? So we have to do the intersection here to actually get that set of points, you know, to say that our analysis will just handle like point 6 in this case. In the cases of like R4 and on these two equivalent sets, right, there the intersection will just return all the points, right? And that's this special case here where like the intersection expression, right, has the same volume as, you know, the set of points in the set expression for the equivalent set, right? And so then you can just, you know, use the set expression as the thing that we're going to actually perform, right? So we call set. So once we get our expression for the set of points we're trying to analyze, right, then we can call set analyze, right? So if we look at equivalent set, it has its own stuff that it needs to do, right? So the first thing you do, you know, in this analyze method is you try to get the equivalent set lock, right? Because you might have multiple different, you know, analyses trying to analyze these equivalent sets, right, all at the same time. So we do have a lock on each of these equivalent sets. I apologize for the noise from my neighbors next door. We do have locks on these equivalent sets to handle the cases where like multiple different, you know, different analyses might be trying to hit this equivalent set. Like say you were mapping R4 and R5 for different point tasks in parallel, right? They might both be trying to access this equivalent set at the same time, right? And so we try to grab the lock for this equivalent set. If we don't get it, you know, we effectively have a way to defer ourselves and build a continuation. But if we do, then we can come in here and actually, you know, try to do our analysis on these equivalent sets. Right, and the first thing we're going to check here, and this will be a little digression here to go off and take a look at this, but we have to check to see whether whether we can actually do the analysis on this equivalent set, or whether the metadata is actually stored on, you know, a remote node. So one thing that I should point out here is that these equivalent sets are actually instances of, let's actually find it here. These equivalent sets are actually instances of the distributed collectible class, right? And the reason for that is that, right, effectively these equivalent sets can be existing on multiple different nodes. So if I come back to my PowerPoint presentation, right, every one of the equivalent sets here might actually have a copy of itself on several different nodes, right? Because you might be mapping tasks or other operations that need to refer to this equivalent set. Ignore the arrows for the moment, but just realize that you might have a copy on multiple different nodes, right? And so they each are going to try and perform their analysis, you know, on their local node first, right? We're effectively doing it locally at first. But each equivalent set only has, to keep things simple, we actually only store the metadata for an equivalent set on one particular node at a time. So even if you might have multiple copies of this equivalent set on different nodes, at most, one of them is what we call the logical owner, or the owner of like the logical state of this equivalent set at a time. So you can actually see this. I'll show you where this this member variable is that actually stores this. You can see equivalent sets are very big classes. Let's see, where is the logical owner space? Yes, here we go. So effectively, this member right here, this logical owner space member on the equivalent set class, records which of these nodes in this set on different nodes is actually the one that stores all the metadata for this equivalent set at any given point in time. And you'll notice that this is not a const member, right? So effectively, it can actually change over the course of your app, while your code is running. And we'll talk about migration here in just a second. But effectively, it stores the currently valid known owner that we know about on the local node, and it might be ourselves, it might be one of our neighbors, right? But effectively, it's whoever we think the current logical owner is of this equivalent set, right? And so in the case that you're in this you're doing this remote analysis check, what this is saying is like effectively, are we the local node, or are we the local equivalent set? Are we on the node which has the actual valid metadata, right? And you can see this test here, right? By the time, if you get here, right, you better be the logical owner of this equivalent set, right? This is remote analysis call should always, defer itself to do something, on a remote node if necessary, in order to, if we're not, right, to effectively be able to send this analysis, to a remote node, if it's not the current owner. Right, but in the case that we are the current owner, well, then we can go call this perform analysis method, which will actually invoke the analysis on this equivalent set, right, while holding the lock and all that other stuff. And then if it wants to, we can go check this migration. And this migration is what's actually going to potentially move the metadata for an equivalent set from one node to another. So let me actually explain a little bit about this migration, and then we'll continue our walk through this this call of perform analysis. But this sort of like realizing that equivalent set metadata can move around is actually one of the important things that can actually happen inside of Legion. So coming back to this picture, right? So think of it like this: like you might have usually you might wherever the equivalent set gets made, let's assume for simplicity it gets made on node 0, that's always the node which will be the first logical owner for this equivalent set, right? But as your program is running, you might see analyses that come in and start to use this equivalent set, or want to use this equivalent set on other nodes. You might want to use it on like node 1 or node 2 or node 3, right? In fact, you might get a whole bunch of them that want to use it on like on node 3 or something like that, right? And so what can happen, right, is that if the runtime sees that lots of analyses are trying to use this equivalent set on node 3, but all the metadata is living on node 0, it might eventually decide that it's worth the cost of migrating the metadata for this equivalent set from node 0 to node 3, because that will make all of those analyses much more efficient, right? Effectively, if they don't have to like detect that they're not local and then send their analysis to a remote node to be performed, right? It'll be much easier if you just move the metadata over here and allow them to actually use it, right? And so what might happen then is that we migrate this equivalent set from node 0 to node 3, and now node 0 will store that like it's moved the metadata over here, right, to node 3, and it thinks that node 3 is now the logical owner, right? So it'll effectively have recorded that update. Now other nodes like node 1 might still think that node 0 is the logical owner, and you can see this like this blue arrow might reflect that, right? These blue arrows are kind of reflecting who different people think the logical owner might be, right? And then maybe you might have some equivalent sets or some analyses come along and want to use node 2, and eventually we migrate this equivalent set over the metadata over to node 2, right? And then some more analyses come along and they might want the metadata on node 1, and so you might try to move the metadata over to node 1, right? And what you see is you actually build up this like path of different nodes knowing how to forward to their most recently known logical analysis, and you might even have this migration taking place in flight, potentially while analyses are actually trying to use this equivalent set, right? So one thing that can happen, like let's say that we have like an analysis that comes along and tries to use the equivalent set on node 1. Right. Well, it says, okay, I'm trying to execute my analysis here on node 1, But the equivalent set has actually migrated over to, I know I'm not the owner, right? So forward my analysis onto the owner. Well, it forwards it to node 0. Node 0 goes, okay, well, I'm not the owner. Forward it on to who I think the owner is, which is node 3, right? And so this analysis, the red arrow is kind of chasing after this migration, right? And eventually, it gets here. It says, okay, node 3 says, no, I'm not the owner. I think node 2 is the owner, right? You forward it over here. The analysis gets over here. Eventually, it'll say, like, node 2 says, well, I forwarded the owner, the metadata onto node 1 to become the ownership, right? And this analysis says, okay, I might go back to node 1 where I originally started, right? And it might discover that, like, it's made it back to itself while the migration is still happening. So you have to handle the case where, like, this analysis chases all the way around and then, might get caught, bypassing the migration while it's in progress. But we have cases for handling that where we effectively detect that we've gone around on a cycle and end up blocking ourselves and waiting for things to stabilize so that we don't keep pointer chasing ourselves around all the nodes. But effectively, nodes these analyses, they come in, they try to use their equivalent set on their local node, and if not, they'll pointer chase, around the nodes to find who the current equivalent set is the owner. And there's also an optimization here, like in cases where you get an analysis that comes to a node and detects that, like, it's not the most recent, it doesn't have up-to-date ownership information. We'll actually forward that information back along this path so that these equivalent sets can update who they think the owner is, and eventually, shorten these paths so that people eventually we develop consensus as to who the owner is of this equivalent set. But these analyses, they come in, they try to use their equivalent set on their node, and then they'll just jump around trying to traverse to remote nodes, right? And so this code here, this is remote analysis code. If we actually take a quick look at it, so I'm actually going to skip a lot of this. Let's actually skip most of this replicated stuff because it doesn't actually apply right now. But effectively, the important part is this part down here at the bottom. And that's the case where, effectively, if we're not the logical owner, we tell the analysis, hey, we think that there's, we actually need to send this analysis to a remote logical owner on a different node to send it somewhere else, right? And so if we go back to look at, like, regiontree.cc here, right? So you do this traversal, right? You might get back a set of remote nodes that you need to go traverse, and then that's when you call this perform remote stage on this analysis, right? To actually go send those messages off to actually do those traversals remotely on a remote node, right? So effectively, like, and we can actually take a quick look at that. So if we actually go look at Legion analysis and we look at perform remote, and let's find the update instances version of this, or update analysis. Here it is, right? So this is the perform remote version, right? And in the case where we have remote stuff that we've got to send, what you'll see is we pack up, all of our state for this analysis for all the equivalent sets we need to talk to on a remote node. This is the node we're going to send it to. We pack out all of our stuff, and then we send off a message to send this analysis to that remote node and perform it. And down here somewhere, we've got the unpacking code that effectively handles this remote update, right, and unpacks this analysis over here. There's a bunch of deserializing stuff here, right? But eventually, we make a new copy of our update analysis, and then we start running it, right? And it does the analyze stuff, and it also checks for remote sets. It might get forwarded, right? In which case, we continue this perform remote, right? So we'll continue forwarding on to the next stuff, and you can go round and round until you actually find the node which actually does have the valid metadata for the equivalent sets that we need, right? And return everything back to where it needs to go when we're done. Okay. Right. So we do perform traversal, and then if necessary we do perform remote. And then once we're actually done, we can actually perform this updates. And so let me just describe this briefly, and then we'll go back and finish out this perform traversal stuff. But since we're here, right. So one thing I should describe is that one thing that this update analysis does is it doesn't actually. The reason you get this call, this stage of the pipeline, the perform updates call, is that if you effectively want a stage for this analysis that knows when all of these traversals, both local and remote, have when you want to know when all of your local traversals are done, right? So you notice this, both the perform remote and perform updates, precondition on this traversal done, event here, right? Which is often a no event, but in some cases can be an actual event. And what this perform updates is actually doing is, if we go back and look at my picture over here, let's actually say we're mapping R4 just like we were doing before, right? And let's say you're mapping some instance, right? And you need to issue a copy, to update your instance A, let's say. And let's say this equivalent set said that, the current valid data is in instance B, and this guy also says the current valid data is in instance B, right? So when you do your analysis of this equivalent set and you say, okay, I need to issue a copy from instance A to, from instance B to instance A to bring my instance A up to date for this region R4. And similarly, I need to issue a copy for these points, from instance B to instance A to bring R4 up to date, right? Well, you may not want to issue those copies separately, right? You might want to fuse them together because then you can get a more contiguous copy of data that you might actually need to issue the copy for, right? By fusing together, 0 to 3 and 4 to 5, Realm might actually prefer that to be fused, right, into one copy so they can do it all at once, right? And so by doing that, that perform update stage effectively says, wait for us to have analyzed all of these equivalent sets, right? And as part of doing this analysis, we're not actually going to issue copies to Realm. We're just going to record that we have to do them, right? And then we're done doing all the traversals of our equivalent sets. Well, then we can go try and fuse together, all of the copies and fills and other stuff that we're going to need to do to group them into the biggest possible set of copies that we have to issue. And then we'll be able to issue them in bulk, to Realm, to make them as efficient as possible, right? So let's see. So if we jump back over here, this perform updates call effectively is giving us a callback, to be able to do that fusion, and we'll take a look at that. Okay, so let's come back and look at where was I? I thought I was in Legion analysis. Oh yeah, here we are. So we're in the analyze method on equivalent sets. Oh, I went past it. Right, so effectively, eventually we get into this, we effectively did our remote check. If we determine we're on the logical owner, we'll actually go perform analysis, right? Not all analyses will trigger, migrations, by the way. So that's what this Boolean return method here is saying. So certain analyses will allow, updating the migration state, whereas others will not. Mostly the ones that mutate state are the ones that check for migration. Things that are just checking for reading and stuff, we don't actually do migration checks for those. Oh, that's not what I want to do. Where is my search? Here we go. So if we search for perform analysis, right, you'll see every one of the analyses classes has this perform analysis thing. And you can see our update analysis class has this perform analysis method here, right? And effectively it just turns around and dispatches to the equivalent set and says, perform the actual update for this particular analysis, right? And you see in this case we return true because we want to do the perform for do the migration check to see if if we've analyzed ourselves, or if it's worth migrating the equivalent set based on how it's being used. But let's go look at update set. Okay, so we're in update set here, which is where we're actually going to walk over an equivalent set and try to figure out whether we have valid instances or whether our instances are currently valid, or whether we have to issue update copies and fills and other things like that. The first thing to be aware of is that you actually probably need to lock your analysis, right? So you recall that we already have a lock on the equivalent set because that happened, above us in the call stack here when we called traverse on the equivalent set. But it's possible that you can actually, one thing that can happen, if I come back over here, our analysis might have tried to take the lock on this equivalent set and realized it couldn't get it, and then deferred itself and built a continuation, and then tried to do the same thing here and hit another contention and built a continuation. So you can actually have your analysis being used to analyze multiple equivalent sets in parallel with those continuations, right? And so this analysis lock, actually locks our analysis object to make sure it's safe to actually mutate the analysis, as part of doing this traversal of this equivalent set as part of this. So you have to be a little careful with your locking here and realizing that you might have your analysis object traversing multiple equivalent sets at the same time, right? And so that analysis lock happens there. Okay, so let's see. I'm waffling a little bit on whether to dive into this method today because this is a pretty complicated method. We'll probably do the first part of this today, and we will probably pick up here a little bit later. But let's actually do this first part of this method here, which is this check for initialized stuff, because that's something that you guys have all encountered pretty often, I think, sometimes. Let me dismiss this stuff down here. And that is one thing that equivalence sets can actually do is they can actually check to see whether you're using an equivalence set with valid data, right? So like, these equivalence sets know, whether there's any valid instances at all for any of the points inside of them, right? And so like, if you're trying to read an equivalence set that has never been written to before by any tasks, right, we can actually detect that and raise an error, right? And similarly, we can do if you're doing read write, we issue warnings, but if you're reading only, right, we issue an error today. And that's actually occurring right here with this check for uninitialized stuff. So effectively, like, if your analysis is being asked to check for initialized, which most of them are, in fact, like the update state one will always check this for check initialized, right? It's actually going to call this check for initialized data, right, to make sure that you're going to be updating an equivalent set that actually has initialized data. So let's actually take a look at how that actually works here. So let's actually look at this check for uninitialized, right? And you can see this actually gets called with multiple different analyses, so it's templated on the kind of the analysis that we're actually doing this check for, so we can record stuff in different ways. But what you're going to see is there's this member data of the equivalent set, initialized data. And so let's actually take a look at that to actually show you the first one of these things over here. So there's a bunch of state on this equivalent set. We're going to look at a lot of these in more detail, but for today, let's just focus on this one, right? And so what this is storing, right, this is storing a set of index-based expressions and the fields that they're valid for, right? And it's storing things that we know we have initialized data. Somebody has written to these in the past so that, the data has actually been made valid. Right, and so we've got a field mask set of index-based expressions saying, these are the points inside of our equivalent set that, are currently valid. So like, for example, in this equivalent set over here, right, maybe you had a task that only wrote to points 0 to 2, right? We would need a different region for that. But like, let's say you had a tiny little region that only wrote, points 0 to 2 and not the third point, right? Well, then we would have an index-based expression that stored the point 0 to 2 and the fields that task had actually written, and they would be stored in this this initialized data set, right? So that we could actually like record that they've actually been written to, right? And so if we go look over here at this initialized data set, what we're going to do is we're going to do a quick check to see, first off, we do a first drill check to do something very simple, which is to say, like, is the set expression, right, the set of all the points already been initialized, right? So if we can find the set expression, for all of the points in this equivalent set, right, in the set of initialized data, well, then we can remove those fields from the set of uninitialized fields, right? This field mask, says these are the fields we want to check for, and we're going to progressively remove the ones that are uninitialized, right, or that are already initialized. So if we get to the bottom and we still have a set of uninitialized fields, well then, that's when we need to record something, right? But effectively, if you've initialized all the fields, right, for all the, or these are a set of points that have been, or these are the fields which have been written for all the points, right? Well, we can very clearly remove those, right? Remove all those from that field mask. And if that field mask is now empty, well then we're done. We didn't find any uninitialized fields, right? Similarly, this expression might not be the same as this set expression, right? You might not be able to do a name analysis, but if you know that it, effectively covers it, right? Well, then you can actually do the same check, right? See if you can. Well, actually, sorry. If you know that it doesn't cover, right, then you actually want to try to see if you can find this expression in the initialized set, right? You might get lucky and find just the name, right? So we're kind of doing a name test here to see if this expression is in this set of initialized data. Right, and if so, right, then we can remove those fields. And again, if we've removed all the fields, well, then we're done. We didn't find any uninitialized fields. Right, and now here's the tricky part, right? So like, effectively, in the case, we should actually be able to fuse these two things together since they're both testing the same if branch. But if you didn't find it by name, the next thing you do, right, is you iterate over all of these initialized data expressions, right? And effectively, the first thing you check is you say, are any of the fields disjoint? If so, there's no point in testing the points because, they're not actually that interesting, right? But if you do, right, if you do find, that there's an overlap, well, then we can compute the intersection between, the set of points, right? And effectively see, is the intersection the same as our expression volume, right? Effectively, we don't actually need to compute the difference. You could have made this a difference. You could have said, like, take our expression that we care about and subtract off, the set of points that we know are valid. And if that set is empty, right, well, then we've done the right thing. But differences are actually pretty expensive to compute in Realm. It's much easier to compute an intersection, right? And so instead what we do is we compute an intersection between these two things. And then you can say, is that expression the same volume as the expression that we're trying to test against? If not, we continue. If they are the same, then we can, filter those fields, right? And again, if you've removed all the fields, well, then you're done, right? And so effectively, this is testing to see, effectively, do you dominate, all the points are all the points that we care about in this expression already valid, right? And if you get down here, well then, and you've still, that means that we still have uninitialized fields that have uninitialized data, and we report those back to analysis, and then it can go and propagate that, back to the application once it gets all the uninitialized, data, and then we report the error message back to the application. But this is an example of like the equivalent set doing, some analysis to actually check for, whether there's initialized data for this equivalent set that we're trying to analyze. One thing I should point out here about this initialized data set, initialized data structure, is that there is at most one entry for any given field in here, right? So effectively, like for all these index-based expressions, each of them will have there will be exactly one entry for each of the different fields in this equivalent set, right? So that's what made this test safe here, to know that we can just do this intersection. If there were actually multiple different, let's say, to give you a real example here, let's say we were mapping points 0 to 2 for like our region for R4, right? But like, effectively points 0 to 2, or sorry, 0 to 1 and then 3 were both stored as separate expressions in this initialized data. Like let's say some prior task had written points 0 to 1 and then some other task had written point 3. But we needed all 4 points, right? So if that's the case, the expressions in here, right, have to store all 3 points together, right? It has to be the union of all those things, right? You can only have one index-based expression per field in these data structures, right? And so one thing you'll see is like when you update this initialized data structure down here, there's some work to like, merge together expressions that have the same fields. And you can see that in this case down here. I'll probably leave this, I'll leave this code, to look at here. This is the code that will actually update the initialized data, effectively to handle those kinds of things. But I'll probably leave that to a future lecture because it gets a little more complicated. So anyway, I think what we'll do the next time is we will probably jump back in with this update set method because it's actually pretty complicated, and dive into some more of how these update analysis actually stores copies and fills, and then eventually merges them together. But hopefully today you guys have a little bit better feel for equivalent sets and how you do analyses on them, and the various kinds of analyses. You can actually go find those and use them for doing different things. So with that, I'm going to stop for today and take any questions anybody has. No questions. I can't have explained it that well. Okay, well, in the absence of any questions, I'm happy to end here. I think Sean is going to be back next week to talk about more Realm copy stuff. So I guess I'll see you guys all next week.